Welcome to our expert session, OT Smart Fusion and how does it work. My name is Thomas Pfaffenzeller. I have been appointed by EOS as a software architect for the EU State monitoring team. In the previous session, we saw the problem caused by overheating. This gives rise to two fundamental problems. It can lead to deformation of parts, and there is a risk of job crashes. With Smart Fusion, a feature of EOS State Exposure OT, EOS offers a real-time heat management solution. In this session, I would like to take you on a little journey behind the scenes. EOS State Exposure OT is a camera-based thermographic monitoring system. This provides real-time process intensity and heat data. This enables us to detect process irregularities which can lead to part defects and to detect overheating within parts. With the OT camera, we capture radiation from different regions of the process. At the top of all, in blue color, we see spatters. These are airborne particles that are ejected from the process air as liquid at the time of recording. Below, in purple color, the welding plum. This is the plasma flame dancing on the top of the process area. In red, the melt pool, the area where the laser beam hits the powder and melts it. And at the bottom, the resolidification zone, an area behind the melt pool in the direction of the laser, where the molten material can cool down and solidify into dense metal. All of these signals are recorded and combined into one image, the OT integral image. We don't measure purely thermal radiation, but the radiation intensity in the 900 nanometer range, which is made up of the emission spectrum of spatter, welding plum, the melt pool and the solidified material. So after each layer we end up with an image which can be interpreted as a heat or energy map for the process. All these four different signals rise with more energy in the process, whereas spatters, welding plum and melt pool are most important if we want to evaluate the process stability. The last one, resolidified material, is very useful to evaluate the overall heat management of the build process. And it indicates whether the material cools down quickly in case of a good heat dissipation or stays at elevated temperature for a longer time in case of bad heat dissipation, indicating heat accumulation and therefore overheating, which, as we saw, can lead to job crashes and unfavorable material characteristics and grain structure. If the part has an elevated temperature level, we can reach the desired window with less energy input. This is the same principle as when heating a soup. If it is already at 80 degrees, we don't need to full power to boil it. If it is only at 20 degrees, we need much more power to heat it in the same amount of time. That is why the laser power is a changing parameter. According to this signal map, we can define a gray value for the standard process, and Smart Fusion ensures that this gray value is kept throughout the build. In the video, we see two different parts being built. The first one on the top is built with Smart Fusion, and the one on the bottom without. Both start out with the same geometry as seen on the right and the exact same process. As we can see in the video, the part without Smart Fusion overheats drastically and starts to glow red because there is no control. This led to oxygen pickup and different microstructures, whereas the part with Smart Fusion on the top does not show a red glowing process. Therefore, not as much oxygen pickup and more consistent microstructure. Please recognize the color of the parts on the right. Note that these are parts specifically designed to overheat, so these are massive thermal bottlenecks by design. On this slide we can see the OT signal of the part with Smart Fusion on the upper graph and the part without Smart Fusion on the lower graph. To generate the image within OT, filtered camera frames are integrated from the 900 nanometer spectrum. This generates a heat map as an image of every layer. As you can see, the signal distinguish themselves a lot. In the upper signal we have a flat line at the gray value set by Smart Fusion with some minor ripples at the thermal bottlenecks. These are the time spans where the Smart Fusion process regulates. The bottom graph shows a very lively signal with up to 5 times the gray value of the standard process. This is a thermal history of massive overheating. So we can recapitulate. Smart Fusion takes advantage of the eostate exposure OT data and controls the energy input in return. This reduces overheating significantly, and this leads to lower stresses, less deformation, less job crashes, less needed support structures, less oxygen pickup, less thermal process instabilities, less thermal deformation. Therefore, as we get more stable material properties. The work principle. We start with an EOS standard process and we assign a target gray value with EOSprint 2. The gray value is the process intensity value that we measure with our OT camera. The measure of how much intensity is hitting the sensor at a given pixel. Smart Fusion will try to maintain the process at this target gray value by calculating the laser power correction factor as LCF image. This is done by checking the gray value of each pixel after exposure and depending on the deviation from the target value. A correction factor is applied. Using this correction factor, the power is then adjusted in the next layer. So, an area of the part that we detect as being too hot will be exposed with a lower laser power. With the control values obtained from OT and reported back to the machine, which can recognize on the left as LCF data, scan vectors are formed with correspondingly adapted power values for the laser. This principle is also used for the Smart Fusion replay function, where we freeze the changes made by Smart Fusion for the next build jobs. The controller values from a successfully built job are fed back into the EOSprint, so that the same build job can be built again with the same laser power values to manage without directly control during the build job. With this feature, repeatable and consistent job results due to the frozen parameters are guaranteed for every future job run. The LCF data is mapped directly on the EOSprint side in scan vectors and is therefore already included in the build job task, which is then sent to the machine. Here we see the homogeneous microstructure for the whole part with Smart Fusion on the left side and without Smart Fusion on the right side. 3 very different types of microstructures and therefore different material properties in the part. This will be discussed in more detail in later expert session. Thank you for your attention.